All right, let me try another good one here. It's a pretty hard one. Been getting a lot of questions on it, and rightfully so. It's number 62. It's a magenta one, and so maybe I'll just put here page 1, chapter 23, problem. What problem is this? To 62, I said. All right, 62. And if you've read 62, it looks something like this. It's got this grid, although they don't give you a grid, they just describe it. But they say that there is a line of charge that is along the line y equals negative 15. So coming down to 15, this is the line, negative 15, and they say from 0 to 40, and they say centimeters, so I'm going to put it in meters here. But from 0 to 0.4 meters, there is a charge that has a charge density of, 35 nanocoulombs. And the question is, what is the electric field at the origin? Now, let's start conceptually here. Maybe you could picture a little chunk of charge right here, a dq. And so this would be the distance away, r, and that would be the electric field. Now, another chunk of charge over here, let me call it a dq. This would be the r, and the electric field would look like that. And sadly, and this is probably why it's magenta, there is no symmetric twin. There is no way we can say, oh, well, the x components are going to cancel off, or the y components are, or something as powerful as, if you saw the video solution to number 60, that one, I tried to argue with you that look carefully for these, because in number 60 we had 8 individual charges and the top 4 canceled off. So what looked like was going to be 8 calculations drops to 4, and even those 4, as we look at the symmetry, dropped to 1. And so what looked like was going to be a hard problem because of the symmetry, it actually reduced to a simple one. This does not do that. And so every chunk of charge does have an x component. In fact, if we maybe kind of look at this one here, and I'll just extend it so I can draw a little bigger in my picture. Excuse me, I'll call that theta. And so that would mean that angle here is a theta. And since you're asking for the electric field at the origin, I've really got 2 calculations to do, because there's going to be an x component and there's going to be a y component. And as I said a moment ago, sadly, I can't simplify any of these, and I got to just do the full calculation. So why don't we do the x component? Starting with the idea of the x component, it's I've only drawn 2 up here, but remember there's a bunch of chunks of charges, and so you would be adding up the x component from each one. And so let me write that in the calculus form. That's what this means, a summation of the x component. And so if you add up all the x components of each individual chunk of charge, you're going to get the total x component, and that's going to go right here. So that's what I'm looking for. What is that x component? And then, of course, since our formula for the an electric field, a chunk, a point, is given by its magnitude, we have to probably change this formula for its x component into its magnitude and then multiplied by cosine theta. So cosine theta. So we can use the formula for magnitude, and then this little factor here is what makes it equal to its x component. And in fact, that is that little factor here. This is the Coulomb's law. So we have Coulomb's constant times the little chunk of charge right there over r squared. That's the little formula for the electric field from a point. And then, of course, we still have this cosine theta. So that's kind of the main conceptual physics of it. I still need to go and kind of, this is where the math and the physics kind of mix, because obviously I have an integral, but ultimately you can kind of see I'm going to be adding along the x-axis. So I need to switch everything, the dq, the r, the theta, all into an x, because I'm going to be going from 0 to 0.4. And so I need to make this into an x, and this into an x, and this into an x. And of course, all of those do depend upon x. You can kind of see that as you move along here, the r is getting bigger and bigger, so the r depends upon where you are on the x-axis. And likewise, the angle theta, here the angle theta would be close to 90 degrees, and then as you move out, it's getting less and less and less. And so again, this has to depend upon x. So let's see if we can figure that out. And maybe I'll start with, I think the easier one here, the r squared. If I kind of drew a solid line on my picture here to represent the r, and remembering this is 0.15 down, then where I am on the x-axis, here or here or here, if I call it x, I can get this length, the hypotenuse, by using Pythagorean's theorem. So this would be 0.15 squared plus x squared. And so that is r squared. Now, maybe the other one that's a little harder, so I'll hold that till last, is the angle. And if you come back up here and you look at cosine of this angle here, of course we originally put it in focused on that, but that one is the same as here. And if I make a little triangle out of this and say cosine, then cosine is this adjacent piece, which is x over that hypotenuse. So this would be x over the hypotenuse, which we just did over here. So this would be 0.15 squared plus x squared to the 1/2. And then, of course, maybe the harder one here is to remember, what do we mean by lambda? What do we mean by this charge density? Well, we mean if you take a little piece, or a big piece, doesn't really matter, but I'll talk about a little piece, and you take the charge on that little piece. So dq is the symbol for a charge on a little piece, and you divide it by the length of that little piece. So if you're saying that this little chunk of charge has a value of dq, I'm also saying it has a length it expands of dx. And then moving that to the other side, saying that lambda dx is this dq. So this should be equal to lambda dx. And so now I have made this important mathematical step, kind of focusing on the physics of the picture. So that's why I said kind of a math physics mixture. We started, I'd say, with, well, I guess we was doing math here, but it was very physical and then has now become a little more mathematical. Now it's going to be all mathematics to finish it. But it was changed the dq into a dx. It changed this into a function of x, and it changed this into a function of x. And so now I have just functions of x. And so I could say go and add up each of these chunks, starting at the first chunk at x equals to 0, and the last chunk at 0.4. Maybe I'll put 0.40. And so that would be the limit there of my integration. And so now it really is just a matter of now complete the math. So like any integral, look for things that are a constant, and of course Coulomb's constant and lambda are a constant, and then we would be left in the numerator with an x dx. And in the bottom, these are like terms. They're not constants, so we can't pull them out, but we can combine them together, and so there's our integral with the limits. And then, luckily enough, this is a fairly straightforward one. This is a u sub. You can kind of see it. If you said u was equal to this part in the bottom there, And so that du would be 2x dx. And we could now then substitute this x dx here for 1/2 du. And we can substitute this as a u raised to the 3/2 power. And that's just a power one. I'll give you another little helpful hint. I know in one solution I actually did the u sub, and the other one I said that there is a quick way, I think, of doing u subs that make them easy. And that is, you know, the whole purpose of doing a u sub is to get rid of that. So stop thinking about that. And then you just have a power function. And that's what we would have here. And then, of course, when you bring it to the top, you got u to the negative 3/2. And so when you integrate a power function, that's simple. You just add 1 to it. So I would just say, let me add 1 to that. And so this would become No, I want to actually do the integral. So Coulomb constant times lambda. And so the actual integral would then be this 0.15 squared plus the x squared to the 1/2 power. See, because that's what you're going to get. You're going to add 1 to the negative 3/2, and you're going to get a negative 1/2. And of course, so I'm putting it down in the bottom. And then here's where you may have a factor of 1/2 or something, but I'm thinking not, because the factor of 1/2 and then the derivative of this 1/2 I think are going to cancel. So what I like to do for u subs, if this helps you, is to ignore this and then just add 1 to this. Remembering this is upstairs, so add 1, and then of course it's a negative 1/2, so bringing it downstairs. And so I think that is the solution if I went through all these steps. And the reason I find it fast to do is I could just add 1 to this and write that down, and then check it to see if I'm missing anything. And so if going from here back to here, if I take the derivative of that, and doing derivatives in your head is pretty simple. I'll kind of scribble it over here on the side so you can see. But if I was taking the derivative of this, I would think of this being upstairs, and I'd get a negative 1/2. And of course, then I would lower it by 1, and so that would make it a negative 3/2, which I'd move downstairs. And then I would have the derivative of the inside piece, which would be the 2x. And see, there's what I was saying. I can see those 2's cancel, and I have the same thing. Oh, with a minus sign. Oh, so I bet there's a minus sign here. Yeah. And so I need a little minus sign. You see, and then that's kind of what taking the derivative checks to see if I, missed a factor of 2 or if I missed a minus sign. But the main part of it is already done. All right, now I'll just put the limits. So if you want to go back and do a u sub, great. If you want to just, if my method of the u sub helps, I think that's something you'll develop with time. Probably here at your point in your education, maybe you should just focus with just doing the u sub. So hopefully I didn't mess it up now that I talked all about it. In fact, I'm just going to just double check here. So if I were to take the derivative of this would drop it down by 1. Okay, so I'd get that. Then, of course, taking the derivative would bring down a 1/2, and then I would get the integral, bring down a negative 1/2, which would get rid of that negative, and then the 1/2 with the 2x would cancel off, and you would be left with just an x. Good. So I'm pretty sure the negative's there, and there's no factor of 2. There's just a factor of 1. That's all the part that you kind of question when you do it this quick way, but that's very clearly the piece. All right. Now, keeping that, close at hand, I'll just put then in my limits, and so here is Coulomb's constant times lambda, and now if we put in our value, we would have a negative 1 over, and this would be 0.15 squared plus 0.40 squared, all that to the 1/2 power, and then minus a negative. We'd have to put in the 0, and that's probably the easy one, because when you put in the 0, that goes away, and you have the 0.15 squared, and then take its square root, so that's just 0.15. And so now I can kind of get out my calculator. These two negatives right there make a positive, so I'll just go 1 divided by 0.15 there, minus, and I'll use that one, 1 divided by, and here's where I'm going to have to put the square root of 0.15 squared plus 0.4 squared, close bracket, and I get about a 4 there. Now let's multiply that by the 35 times 10 to the negative 9. And then multiply that by Coulomb's constant, which is 9 times 10 to the 9th. And so I get 1,362 newtons per Coulomb. So that is the X component. Now, I guess I should be a little careful here because I also did that as the magnitude of the X component. So this is going to be in the negative direction, but I'll put that at the end. Now, a little harder calculation is the second half here, which is the Y component. And so maybe I'll go a little bit faster, but I'm hoping you kind of get the idea, especially now at the end of the homework. I would just say the Y component is the sum of all the Y pieces. Okay, there. And I'd get the Y piece by saying take its magnitude and multiply by the sine of the angle. Okay, so the sine of this angle. And again, we really needed to do that because the formula for the electric field is given in terms of its magnitude. And like I did for the X component, we're back here with this integral. In fact, it should be really the same logic and thinking. It's just we had a cosine and now we have a sine. And so now to actually do the integral like we did back for the X, we have to switch everything to an X. And so this would really be the same logic. This would just be lambda dx, okay. And the distance away would be that same logic. It would be 0.15 squared plus x squared. That would be the R component. And then the sine, coming back to our picture, would be opposite. So this would be the 0.15. And like we did here, let me save a little bit of time. Instead of writing it, and just put 3/4. Okay? And of course, we're still adding the same limits, right? We're still adding the chunks from here to here. The only difference is we've now done the vertical component. So, kind of like we did back here, let's actually now solve the math. There would be a Coulomb's constant, there would be a lambda, and there would be a 0.15. And then we would have this integral that has a dx in the top without an x. See, I say without an x because that's really the difference then between the x component and the y component. The difference between having the sine and the cosine. And then, of course, we have this in the bottom, which is the 0.15 squared plus the x squared over the 3/2. And I'll put my limits. Now let me say a little bit about this integral. This is a harder integral. This does not have the beautiful u sub in it, right? The u sub you see when this is the derivative of that. So when one piece is the derivative of another piece, that's a perfect recipe for a U sub. We don't have that this time. We do not have the derivative anywhere in here. We have this, but we don't have its derivative. So those are much harder, and this one turns out to be a great one to do by a trig sub. And if you go back to the video solution in number 29, I ran through the U sub. So if you want to see the whole U sub worked out, fine. But let me take this as an opportunity to say the same thing that I said in the Zoom meetings and when I did the solution for number 29, is that keep this in mind, that these harder trig subs and some of the other ones, common factors are products, those, feel free to look them up. So that's what I'm going to do here, and you can do that during the exam. I'm going to look this one up. And so in the survey book, it's in Appendix B, but you can do it with Google. If I remember, it's table B5, and it's on page 1447. And so I'm just going to look now at the solution. And so this actually comes out to be x over, and I shouldn't say solution, the integral of this without actually doing the U sub. And it would be 0.15 squared, and they label that as an a because they have like an a squared plus an x squared in the table B5. And then the plus x squared, and, I didn't write that well. Let me try that again. There's an x over, and first they have the 0.15 squared. Then they have a square root, and then it's an x squared plus a 0.15 squared. And so that would be evaluated from 0 to 0.14. And so now we can put it in and finish the problem. The 15s would cancel off. In fact, I'll just put the Coulomb's constant, the lambda, and the 15 together. And then when I put in the limits, I have the 0.14 here over the square root of 0.14 squared, 0.15 squared, square root, and then technically minus a 0. And so now if I grab my calculator here, I can put these in. Maybe I'll start with this, 0.4 divided by the square root of 0.4 squared plus 0.15 squared close, and I get that. Let me multiply that by Coulomb's constant. Let me multiply that by the charge density, which was the 35 nanocoulombs. And let me divide that by the 0.15, and I get a 1,966 newtons per coulomb. So the final answer would be this. The electric field, the total electric field at that point would be, and so coming back up to here, here's the x component, as we said, would be the negative direction. So it would be a negative 1,362 newtons per coulomb in the I hat direction. And I should, and plus, sorry, you guys got to get to the picture, but the picture, see the x component is negative and the y component is positive. And so that's a positive, what we just solved for, 1,966 newtons per coulomb in the j-hat direction. And so, yay, I think I did it right there. So, great.